Okay, in this video, we're going to talk about how to draw modulus graphs on a coordinate plane. Supposing I asked you to graph f of x equals the modulus of x plus 1. You need to be able to come up with your own domain, and there is a suitable domain. You need to figure out what a suitable domain is, and you need to draw yourself a graph. Before we think about how to draw a modulus graph, let's just think about how we would draw the graph f of x equals x plus 1. Again, let's just make up a domain here. Imagine if I was asked to draw the graph of f of x equals x plus 1 using x values from -3 to 2. I'm just going to work out all of my values here and look at what the coordinates for this graph would be. So in a basic question, if you just had a normal curve like f of x equals x plus 1, if I asked you to graph it in the domain -3 to 3, you might come up with a table like this. What I have here are all the x values from -3, and I'm using all of the integers from -3 to 3. The function itself is x plus 1. So in each case I subbed in a different value for x and added 1, and I got the corresponding f of x or y value. And in each case then I wrote out my coordinates. For example, the first one is -3, -2, and the last one is 3, 4. Now that I have all of these coordinates, I can draw the graph of this line. If I plot those coordinates on a coordinate grid, it looks like this. It's a very basic linear graph, f of x equals x plus 1. I've just subbed them in. For every x value, the y value is 1 larger. So if x equals 1, y equals 2. If x equals 2, y equals 3, and so on. That's a basic graph that I could give to people in second year that's relatively straightforward. But if I change this, and if I put modulus signs around it, it completely changes the meaning of the graph. If I asked you to graph f of x equals the modulus of x plus 1, I wouldn't give you a domain. You should know what a suitable graph is for f of x equals the modulus of x plus 1. The graph is not particularly different from this one, but the issue lies in the fact that I've told you that the modulus cannot be negative. I cannot have a negative. Like, it's impossible for me to say that the modulus of something is equal to a negative value. I cannot have the modulus of x being equal to -4. It's just not possible. It's okay for me to have a negative thing in the modulus. If I have the absolute value of -4, then that's fine. There's nothing wrong with that, because the absolute value of -4 is in fact equal to +4. I would just ignore the sign, and the absolute value of this is just 4. So you need to realize is that it's okay to have a negative value inside the modulus, but it is not possible for the modulus of something to be equal to a negative value. It has to be positive. So it's impossible in this case for f of x to be negative. The x value can be negative, that's grand. I could have -1,000,000 inside my modulus sign, but the absolute value of -1,000,000 would be equal to +1,000,000. So this is not allowed. This is not possible. This is fine. It's okay to have a negative in your modulus, but it's not possible for it to be equal to something negative. In terms of a graph, that means that the y value can never be negative. It is not possible to draw a modulus graph that goes below the x-axis. The x values can be positive or negative, but the y values cannot be negative. It's really important I stress that everything we do in this video is based on the premise that the y value in a function like this cannot be negative. So obviously that means that this section, when I go below the x-axis, there's something wrong there. So let's first think about what happened when we subbed in x equals -2 when there was no modulus signs. When there was no modulus signs, to get f of -2, it was simply equal to -2 plus 1. And in that case, I worked out that f of -2 was equal to -1. And that's where I got my x value. I got the point -2, -1. However, it completely changes if I introduce a modulus sign. If in fact f of -2 was equal to the modulus of -2 plus 1, I would have ended up with f of -2 is equal to the modulus of -1. If you have a negative value inside your modulus, you simply ignore the negative. So in this case, if there's a modulus there, I'll say that f of -2 is equal to +1. I'll just ignore the presence of the negative. Which means that as this graph goes on, instead of going to -2, -1, it actually goes to -2 plus 1. I simply ignore the presence of the negative y value and I make it positive. So the line I'm about to draw here is actually going to be a mirror image of the bit down here. It's just like axial symmetry in the x-axis if I folded the x-axis over. Now similarly, let's investigate what happens if I sub in the x equals minus 3. If I sub in x equals minus 3, I would get f of minus 3 is equal to the absolute value of minus 3 plus 1, or in other words, f of minus 3 is equal to the absolute value of minus 2. But if there's absolute value signs there, I simply ignore the presence of the negative, and I'll instead say that f of minus 3 is equal to plus 2. So rather than having minus 3 minus 2, I simply have minus 3 plus 2. So the original line without the modulus signs looks like this. But if I introduce the modulus signs, then this part of the graph is no longer present, and instead my graph goes in this direction. So for this video, we're going to be drawing graphs like this, modulus graphs. If you have f of x equals the modulus of something, and invariably they're going to look like a V shape. So let's now have a look at how we could draw modulus graphs without drawing a table at all. Let's have a look now at this second example. Supposing I asked you to draw the graph of f of x equals the absolute value of x minus 2. You'll notice in this case, I'm not going to bother writing out a load of different points. In the previous example, just to introduce it to you, we found a load of different points, but we only need actually to find 3 points in order to draw this graph. If it's a modulus graph, I know that it's going to move towards the x-axis, then it's going to move away from the x-axis. It will never go below the x-axis because the y value can never be negative. So 100% I know the negative part of the y-axis is actually irrelevant. I'm definitely not going down there. I'm only dealing with the x-axis and above. To start these graphs off, you always need to identify where does this graph cross the x-axis. I know that on the x-axis, y is equal to 0. So for any function, in order to identify where it crosses the x-axis, you simply sub in y equals 0. The function is given as f of x equals the absolute value of x minus 2. But in order to identify where it crosses the x-axis, I'm going to view this as if it's just y equals x minus 2. I don't need to bother with the modulus signs here because I'm only trying to identify when y equals 0. The modulus is allowed to be equal to 0, that's fine. So I actually don't need to include the modulus at all when I'm trying to find where it crosses the x-axis. Where it crosses the x-axis, I know y equals 0. So I'm simply going to sub into my function, sub in y equals 0, and find the corresponding x value. If I do that, I'll get 0 is equal to x minus 2. I add 2 to both sides to find the value for x, and I work out that when y is equal to 0, x is equal to 2. So I know that the point where this graph crosses the x-axis is the point 2, 0. Now you'll notice that in this question I didn't give you a domain, and in the leave insert I think it's unlikely that you'll be given a domain because you need to deduce a suitable domain for yourself. And basically a suitable domain, you work out where does it cross the x-axis, and you know you need to go a line in this direction and a line in that direction. So essentially at this point, once I've identified where it crosses the x-axis, you can kind of view this as if you just need to draw 2 lines. I need to draw a line going up here and a line going up here. You should remember from coordinate geometry of the line that in order to draw a line you need 2 points. So let's imagine first of all that I want to draw the line to the right hand side of the point 2, 0. I already have 1 point on it, I just need to get 1 more and I'll be able to draw my line. So if I just get 1 more point, 1 more value to the right of the point 2, 0, then I'll be able to draw my line. So you take any x value bigger than 2, 3 or 4 or 5 or anything at all, but logically probably the easiest one to use is to just use 3. So what I'm going to do now is I'm going to sub into this function and I'm going to work out what is the y value when x equals 3. So let's just sub in and see what it looks like. If I was to do that, I could write this as f of 3 is equal to the absolute value of 3 minus 2. Essentially just instead of x I'm subbing in 3 minus 2. So that would tell me that f of 3 is equal to, and in my absolute value signs I have 3 minus 2, which is simply 1. Now remember, the absolute value signs are there only to ensure that whatever's inside is positive. And in this case, that's 1. 1 is positive. I have no issues with that. So I can simply say that f of 3 is equal to 1. I can simply ignore my modulus signs. Or in other words, when I subbed in x was equal to 3, my y value works out as 1. That tells me that a point on this function is the point 3, 1. X equals 3 and y equals 1. So I could just plot that. X equals 3 here and y equals 1 here. Now, obviously you'll have a 2-scale diagram, so it'll be really accurate. And at this point, when you've plotted 2, 0 and you've plotted 3, 1, you'll simply use your ruler and you'll draw a line going in this direction. And that's half of my modulus graph drawn. Now I need to draw the other half of my modulus graph. The other half of my modulus graph is going to be a line moving towards 2, 0, moving down towards 2, 0, but once again it's going to be above the x-axis. So I just need to take any x value smaller than 2. I could take 1, I could take 0, minus 1, it doesn't really matter. But logically the one that I should take here is, I'm just going to take x equals 1. And I want to find the corresponding y value when x is equal to 1. So this time I'm trying to find f of 1. And if I sub in for f of 1, it's the absolute value of 1 minus 2. Now, so f of 1 in this case, in my absolute value signs, 1 minus 2 is obviously minus 1. Now this is where the modulus signs actually come into play. The modulus signs are there to ensure that whatever is inside it is positive. Minus 1 is clearly not a positive number, so I'm just going to ignore my minus. And I'm going to change it to a plus 1. So f of 1 in fact actually becomes 1 as well. That tells me that in this function, when x is equal to 1, the corresponding y value is also 1. That tells me that the point 1, 1 lies on this function. So what I can do is I can actually just plot the point 1, 1. X equals 1 and y equals 1. And when I do that, I now have 2 points on my other line and I can draw it. Once again, you'll be using a ruler here and you'll draw your line and it'll go up in this direction. Essentially, the shape of all of these graphs, draw the graph of f of x equals the modulus of x minus 2. Essentially, they're all going to look like this. I want you to just imagine something here. Imagine if I had asked you to draw the graph of f of x equals minus the modulus of x minus 2. If I had simply put a negative in front of the modulus, that means everything would be reversed. That means everything would be below the x-axis and it would look something like this. So it'd be interesting to challenge yourself, see if you can answer this question again, except there's a minus in front of the modulus signs. That would mean that everything that you put into the modulus has to be positive, but then you multiply it by a minus, so they all have to be negative. So if you were to do minus the absolute value x minus 2, your graph would be basically a mirror image of this one mirrored through the x-axis. I'm going to give you a few questions now that I want you to try yourself. Okay, so I'm giving you 2 questions here. These questions represent the way that I imagine a leave insert exam question on modulus graphs could come up. In the first one, I want you to draw the graphs of f of x equals the modulus of x minus 3 and g of x equals 2 on the same coordinate grid. So the important thing for this question is that you're able to draw your V-shaped graph for the modulus of x minus 3. And g of x equals 2 is simply a horizontal line where y is always equal to 2. Once you've drawn your 2 graphs, you then need to hence find the range of values of x for which f of x is greater than g of x and for which g of x is greater than f of x. The second question is similar to that. I want you to draw the graphs of h of x equals the modulus of 2x plus 5 and g of x equals 3 on the same coordinate grid. Then I want you to hence find the values of x for which h of x is equal to g of x. So I want you to pause the video now, attempt these 2 questions yourself, and then compare them to my solutions. Okay, so in this question, it's key to have an accurate graph drawn. So I've drawn myself an x-axis and I've labelled a few x values and a few y values. What we need to do first is to draw the graph of f of x equals the modulus of x minus 3. A modulus graph like this is a V shape. It's going to go to the x-axis and then it's going to go back up. It's essentially 2 lines that meet at a specific point on the x-axis. In order to draw this modulus graph, the first thing I want to do is identify where does this function touch the x-axis? I'm going to view this as y equals the modulus of x minus 3. I find that when you're drawing a graph, it's easier to just think of your f of x as just your y, or your g of x is just your y. The first thing I need to do is to work out where it touches the x-axis. And if I'm doing that, what we can actually do is we can more or less ignore the modulus signs. Imagine if we just had the line y equals x minus 3. In order to identify where it touches the x-axis, we can let y equal to 0. If I let y equal to 0, I get 0 equals x minus 3. And in order to get x on its own, I would add 3 to both sides, and I could say that x is equal to 3. That tells me that in this function, it touches the x-axis when x equals 3, y is equal to 0. So the point 3, 0 is my point of reference for drawing this function, because I know there's a line going up in this direction and a line going up in this direction. In order to draw a line, you need 2 points. So I have the point 3, 0. In order to get another point on the line that goes to the right of 3, 0, I need to just find one more point. I'm going to sub in x equals 4 into my original function, and I'm going to see what the corresponding y value would be. If I sub in x equals 4, I would get f of 4 is equal to the modulus of 4 minus 3. The 4 minus 3 is obviously just 1. Remember that the only reason the modulus signs are there is to ensure that the modulus, whatever you get inside, you just make it positive. However, 1 is already positive, so I don't need to change it. So I can simply say that f of 4 is equal to 1. So that tells me that when x equals 4, y equals 1. So the point 4, 1 lies on the function f of x equals the modulus of x minus 3. Now I need to, so once I have those 2 points, I can simply draw myself a line up, and that's that one covered. But now I need to draw the line that goes to the left of the point 3, 0. In order to do that, I need one more point. I need to sub in an x value smaller than 3. Any x value will do, but obviously the easiest one is x equals 2. So I'm now going to sub in, and I'm going to work out what is f of 2. In order to do that, I'll get the modulus of 2 minus 3. 2 minus 3 is obviously just minus 1. And if I want the modulus of a negative, I just ignore the negative. The modulus of minus 1 is in fact plus 1. So I can now say that when x equals 2, y is equal to 1. So I also know that this point, the point 2, 1, lies on the modulus f of x equals the modulus of x minus 3. I'm now simply going to use my ruler, and I'm going to draw my line up in both directions, and I've started by drawing the function f of x. Okay, so once we draw in our lines, we've accurately drawn the function f of x equals the modulus of x minus 3. And that's the only difficult part about this question. The second thing I need to do is I need to draw the graph g of x equals 2. If you have looked at our coordinate geometry at the video we did where we revised junior cert coordinate geometry, you should remember that if you have a line in the form y equals 2, that's simply a horizontal line. Any horizontal line can be written in the form y equals whatever. Our reference there is that the equation of the x-axis is simply y equals 0. So if I have the line y equals 2, you would obviously use your ruler and you would draw a line that goes through y equals 2. Essentially, every single point on this line, the y coordinate is 2. So if it's just y equals a constant, then it's a horizontal line. So in this case, my f of x is the v-shaped function, while my g of x is simply the blue line. You would need to indicate that to your examiner. So I could mark in that g of x is the blue one and that f of x is the black one. Now, so that's the difficult part. Now we can draw our attention to the second part of this question. We were asked to hence find the range of values for which f of x is greater than g of x, and the range of values for which g of x is greater than f of x. F of x is greater than g of x when the black line is above the blue line. G of x is greater than f of x when the blue line is above the black line. So as you can see, this section here, f of x, the black line would be above the blue line. Obviously this keeps going on, it keeps increasing towards in this direction, it keeps increasing in this direction. This section here, f of x is greater than g of x. However, in the bit in the middle, the blue line is above the black, so that means that g of x is greater than f of x. In order to work out these ranges, we need to accurately work out the points of intersection of the black line and the blue line. Now, if you've drawn yourself an accurate graph, you should be able to just read it off. However, I would always tell students you need to verify this algebraically. So what we should do is algebraically identify the points where the black line and the blue line intersect. In other words, I want to know when is the function f of x equal to the function g of x. I know that the function f of x is the modulus of x minus 3. And I know the function g of x is equal to 2. Now I just have a question like the ones we were doing in the previous video. I simply need to solve this and I'll get two x values that will correspond to these 2 points. You have two different ways of eliminating your modulus here. You could take plus or minus in front of the left, or you could square both sides. What I'm going to do is I'm going to square both sides. I can say that x minus 3 squared is equal to 2 squared. In other words, I've simply, in order to eliminate the modulus, I've squared it, because if you square it, it's definitely positive. But if you square the left-hand side, you also need to square the right-hand side. If you multiply x minus 3 by x minus 3, you'll get x squared minus 6x plus 9 equals 4. Clearly I have a quadratic equation here, so I would subtract 4 from both sides and I go to get x squared minus 6x plus 5 equals 0. If I factorize this, the factors of this quadratic are x minus 5 times x minus 1. If I let each factor equal to 0 and get my roots, I would get x equals 5 and x equals 1. That tells me that when x is equal to 1 or when x is equal to 5, the functions f of x and g of x are equal to each other. So that means, and if you've drawn an accurate graph, you would have been able to read it off anyway. That means that the x value at this point is 2. Sorry, the x value at this point is 1. And it means the x value at this point is in fact 5. Remember that every single point on the blue line, y is equal to 2. So I know this is the point 1, 2, and this is the point 5, 2. I actually don't even need the y values to answer this question, because let's have a look at what they actually asked me to do. The first thing they asked me to do was to identify when is f of x greater than g of x. F of x is the black line and g of x is the blue line. The black line is above the blue line in this region and in this region. It is two separate regions, which means I need two separate answers. I was asked for the range of values of x, so I'm only concerned with the x values. At this point, x is equal to 1. So any x value to the left of 1, the black line will be above the blue line, which means one of the answers to part 1 is that when x is less than 1. If I take an x value less than 1, I'm talking about to the left of 1, the black line will clearly be above the blue line. But there's a second region. Also, when I go beyond to the right of this point of intersection, the black line is above the blue line. At this point of intersection, x is equal to 5. So the range of values of x, for which the black line is bigger than the blue line over here, the x would have to be bigger than 5. So if I take any x values that are larger than 5, or in other words, if x is greater than 5, like 6 or 7 or 8, or any value bigger than 5, the black line would be above the blue line. Now let's look at part 2. In part 2, we're asked when is g of x greater than f of x. G of x is greater than f of x when the blue line is above the black line. The blue line is above the black lines between the 2 points of intersection. If I take an x value between 1 and 5, then the blue line will be above the modulus that I've drawn, which means this is just one answer because it's only one region. In this case, if x is smaller than 5, so if x is less than 5 but larger than 1. If x is greater than 1 but smaller than 5, g of x, the blue line, is above f of x, the black function. So that's all that we needed for this question. That's the way that I think this kind of thing is likely to come up. Let's move on now and look at part 2. Okay, so question 2 was similar enough. We were asked to draw the graphs of h of x equals the modulus of 2x plus 5 and g of x equals 3 on the same coordinate grid. Once again, this is clearly a V-shaped graph. So the first thing I need to do is identify where does this function touch the x-axis. So I would simply view this as y is equal to 2x plus 5. In order to identify where something touches the x-axis, you sub in y equals 0. So in this case, I would have 0 is equal to 2x plus 5. Subtract 5 from both sides in order to isolate my x, and I'd get 2x is equal to minus 5. I divide both sides by 2, and I would get x is equal to minus 5 over 2. Or in other words, minus 2.5. So I can tell that this modulus graph touches the x-axis at minus 2.5, 0. So that's my coordinate, that's the point. I know there's going to be a v-shaped graph in this direction and a v in this direction. So I need two different lines. What I can do now is I can simply sub in another x value to the right of minus 2.5. It really doesn't matter which one, although I think it's risky to use minus 2 because it might be too close. If you're plotting 2 points that are really close together, there's a lot more scope for inaccuracy. So what I would suggest is to actually sub in x equals minus 1 rather than subbing in x equals minus 2. Let's have a look at what happens to this function if I sub in x equals minus 1. In this case, I could say that h of minus 1 is equal to the modulus of 2 times minus 1 plus 5. 2 times minus 1 is minus 2, and minus 2 plus 5 simply gives me 3. So that tells me that h of minus 1 is actually 3. So I know that when x is equal to minus 1, y is equal to 3. So in this case, I know that the point minus 1, 3 is on the line. And I can now, if I join these up using my ruler, that's half of my modulus graph drawn already. Now what I need to do is to draw a line that is to the left. Draw a line to the left of this point of intersection. Once again, you could use minus 3. However, just those 2 points, you'd have 2 points really close together, so it would increase the probability that your line is just completely off. In this case, I'm going to sub in minus 4. That tells me that I want to find h of minus 4. If I sub in h of minus 4, that's simply equal to the modulus of 2 times minus 4 plus 5. 2 times minus 4 is equal to minus 8, and minus 8 plus 5 is minus 3. So that tells me that h of minus 4 is in fact the modulus of minus 3. The modulus of minus 3 is plus 3, because I'm just going to ignore the fact that that's a negative. That tells me that the point minus 4, 3 lies on the line. So if I plot my point minus 4, 3, it must be there. Now I can simply use a ruler and join up these 2 points, and I'll have drawn the function h of x is equal to 2x plus 5. So when I join up my lines, I get the familiar v-shaped function h of x equals the modulus of 2x plus 5. Now what I need to do is draw the graph g of x is equal to 3. Once again, you should view this as simply y is equal to 3. Y equals a constant is a horizontal line. And it's at the point, so you would use your ruler and you would draw yourself a line that goes through y is equal to 3. Now, it's only a coincidence that the points I found happened to be actually that minus 1 was 3 and then minus 4 was 3. We were lucky in this case. That means we can actually answer the question straight away. That was the first part of the question, but then it said to hence find the values of x for which h of x is equal to g of x. Obviously, it's like there's 2 scenarios here. The exam question might say use your graph to identify the points. If I was to use my graph here, I could say that for this answer, h of x is equal to g of x when x is equal to minus 4. Or use my graph, I could say that h of x is equal to g of x when x is equal to minus 1. However, we were just lucky in this case. So what I want to do, that's using the graph. But let's just look at algebraically how we could verify when h of x is equal to g of x. So if you were asked to verify this algebraically, you would let h of x equal to g of x. H of x is the modulus of 2x plus 5 and g of x is 3. Once again, you could just take plus or minus in front of the left, split your page in 2, and you get the same 2 answers. But I've opted to square both sides. When I square the left, I get 4x squared plus 20x plus 25, and when I square the right, I got 9. So I subtracted 9 from both sides and got myself a quadratic equation. At this stage, I realised that I can divide everything by 4 to make my life a bit easier. And I got x squared plus 5x plus 4 equals 0. If you factorise and solve your quadratic, you get x equals minus 4 and you get x equals minus 1. So that's verifying algebraically what our graph has already told us. So that's all that I want to talk to you about in terms of modulus graphs. So I think we're ready to move on now.